So now in this video I thought we would go over an old diagram that I got. So if you're learning about batteries or whatnot, you're going to learn that batteries are actually made up of cells. So even though often we call individual cells batteries, if they come in a can like this, technically they're a cell, but we'll still say like battery. You know, you might say give me a AA battery. You actually mean give me one cell if it's just one. When you combine them together, that's when it technically becomes a battery, but we still refer to cells as batteries. So the cell, depending on its chemistry, has a certain amount of voltage, and mostly depending on its size, but it's influenced by chemistry, is its capacity, how much current it can provide over a period of time right there. Because if you're not using it at all, it's going to last, you know, like a really long time. It's going to stay fully charged. And there will be like a time period, but it's like a really long time. It's basically staying fully charged if you don't use it. And if you use a lot of current, it's going to discharge really quick right there. So if it happens to say a particular cell that it's 2 amp hour or 2000 milliamp hours, what that means is that if it can provide 2 amps of current, then you know it'll last about an hour. And you know, that's kind of a lot of current. The battery or the cell might overheat. Just be aware of that. But we're looking at that time period. You could do like 1 amp, again, if that is safe, for 2 hours. Or, you know, if you have a cell that's really powerful, it can provide a lot of current, you could provide like 4 amps for half an hour. You know, that's how that math goes. The current and the time, when one goes up, the other one goes down. Hopefully that makes sense. And then how much total power, that's wattage right there. Now, if the voltage is fine, but the amount of current that it can provide before it discharges. And alkaline batteries are not rechargeable. They used to make ones, so that's when you throw them away. There's also rechargeable batteries. So if you want to get an idea of how long you could use the cell before you got to recharge it, that's when you look at the capacity right there. So if it's not large enough for whatever reason, or you know, if a single cell, you don't want to, you know, try to pump 2 amps out of it, then what you can do is split up how many cells are pumping out that current and for how long. So that's when you put them in parallel. So very important that they're all at the same voltage, the cells, whatever type of cell you're using, or you know, if you're connecting batteries or whatever. Before you connect them in parallel, they got to be the same voltage. Maybe like 1.4 and 1.5 will be okay, like a 0.1 volt difference, but that's kind of the limit I set. You want them as close as possible when you connect them. The one with the higher voltage will pump current into the battery or the cell with the lower voltage, and you'll have waste heat, and maybe that'll be bad for them. Maybe it'll be too much heat. So try to keep the voltage as close as possible. Again, I think 0.1 volt is okay difference. They don't have to be perfectly the same. And you could use like a little resistor to equalize them a little bit before you connect both sides. Because you got to get all negatives together, all positive together. But if you put 3 of them in parallel, you'll end up with about 3 times as much current that they can provide. And also each one of them is providing about 1/3 of the current. And thus they're not going to get as hot, you know, at a given current as if you're pumping it all out of one of them. So yeah, you'll get about 3 times as much current that you can provide, and total current. So you can provide about 3 times as much power altogether. Now, what's more common of an issue is being able to power a circuit, like in this case, with enough voltage. So like alkaline cells, you're only working with about 1.5 volts when they're pretty charged. And again, it'll be slightly higher, probably like 1.6 when they're fully charged. And it will go down over time as they discharge. You just throw them away when they're too discharged. There used to be rechargeable alkaline batteries, but now you just throw them away. So you want to make sure that you get the most use out of them you can. But in any case, if you need voltage like a green LED or blue LED, you're going to need about 3 volts just to light the LED. So of course 1.5 volts is not enough. If you have a red LED, you need 2 volts, but it'll probably glow a little bit at 1.5 volts. But in any case, if you got an LED, probably going to want more than 1.5 volts. So then you connect them in series like this. So one of them, you got the negative as the negative side of the circuit. Then its positive goes to the negative of another battery. that other battery's positive goes to the negative of yet another battery. And then its positive, whichever cell or battery is the last one, becomes the positive side of the circuit right there. So all three of them are going to push their charges, push the charges that goes through the entire circuit. All three of them are going to push. So ultimately you end up with, in this case, 3 times the voltage. Now the current still flows through all three of them. And so if each one of them can push 2 amp hours of current, then if you have 2 amps coming out of here for an hour, each one of these is going to provide 2 amps for that hour. So they're all going to discharge, as if they were by themselves. They only care about how much current is going through them. They don't care how many other batteries are also passing current. They're going to discharge at the same rate. So you get 3 times the voltage, but the same current as a single cell, total amount of current that you can provide. So you got 9 watt hours right there, just like with the parallels. So now what if that's not enough, the 2000 milliamp hours? Then what you do is instead of just a single cell right there, for each one of these 3 cells, instead you would put these 3 cells in parallel. So you take these 3 parallels, put them there, and then another 3 cells in parallel, put them there, and then another 3 in parallel, put them there. So that would be series parallel. And so you would end up with, then you would get 3 times as much power that you could get, 6,000 milliamp hours, and you'd get 3 times as much total wattage as this if you made each cell parallel as well, 27 watt hours. Just be aware of that. So yeah, in any case, moving on. When it comes to the load, so that's basic battery stuff. Keep watching combining battery videos if that was a little too much for you. Otherwise, that could be reviewed too if you've already studied it. Very important you understand that if you are combining batteries, you need more voltage and current than what a single battery or cell can give you. So out of this load here, we combine those batteries. As I said before, we need enough batteries to light the LED. So in this case, we're going to need at least 2 cells in series to get 3 volts, and then more so that we can get more current than just the bare minimum. And so we need a resistor to absorb some of the power provided by more voltage. If you get too much current going through the LED, it's going to burn out right there. And so we got a resistor ultimately to limit current. 10 milliamps is probably fine even for a red LED, and it's probably going to make the green or blue LED pretty bright. But the battery is going to discharge over time. So that's probably okay in this case. So with only 4.5 volts, probably 150 ohm would be fine. Out of this 4.5 volts, LED drops about 3. That leaves about 1.5 volts across the 150 ohm resistor, which gives us 0.01 amps of current. I did the math down there. Now, it's consuming power, of course. As I said before, as current flows through, the circuit is going to discharge the cells or the batteries. And so what we got here is the wattage of the entire circuit right there. So as far as the batteries are concerned, they're providing 4.5 volts at 1 amp, or 0.01 amp, right there. So at any given time, well, it's, the batteries are pretty charged there. We got 0.045 watts of power being consumed right there. And so yeah, you can look at watt hours, how many hours that will last, or amp hours, how many hours that one will last right there. Now, out of that 45 watt hours, be aware the LED is consuming a certain amount of power. So if we want this much light that 10 milliamps provides, that's the power the LED is going to consume no matter what. If that's what we're asking out of it, that's how much power we're going to consume. Now, the resistor, we can, adjust its value and adjust the voltage that we use to set that current right there. And so whatever the resistor is doing, that's just waste heat right there to limit the current. And the heat that it provides is wasted energy, is probably a better way to say it. So we'll look at how much of this power is being wasted. 1.5 volts across the resistor times 10 milliamps, which is 0.01 amps, is 15 milliwatts right there. So that would be 0.015 watts if you actually did the math out right there. But yeah, about 2/3 of the energy from the battery is light, which is what we want. And then about 1/3 is waste heat right there in this particular circuit. So sometimes that comes into account or whatever, how much waste heat you got. You want to lower this as much as possible. You want to get as much of the battery power to lighting the LED as possible. Now, of course, this is a low power circuit. You don't generally worry too much about the waste heat. We're not wasting like a ton of money here. But larger systems, you would want to get the waste heat down to a minimum. You want to get as much of the powering the load as possible. And so yeah, as I said before, if you have a 2 amp hour battery, you can expect about an hour of power if it's providing 2 amps. Now, that cell or battery or whatever actually has to be able to provide that. It probably doesn't. Generally, they're intended for low power for long periods of time. They can get too hot. That's just kind of a guideline for how long you can expect it to last. You're probably going to be like AA cells or something in the milliamp hour range right there. So if you happen to have a cell, maybe it's a C cell or a D cell or something, I don't know. But if it can provide 2000 milliamp hours and you are using 10 milliamp hours, I must have wrote 2000 there, but you can expect about 200 hours of light. And if you need 45 milliwatt, oh, you could do the milliwatts as well if you want to calculate it there. That's what I did down there. And you know, so you could go either way. But yeah, it's pretty important to have an idea. You know, batteries are not also like perfectly 2000 milliamp hours. Maybe you'll get a little bit more out of it. Maybe they lied. Maybe you won't even get that much. Also, the voltage goes down as you use them. You got to be aware of that. So things can get complex there. So you kind of want to oversize your battery for what you're going to use. But it's good to get a general idea. So if you know the wattage of the battery, the watt hours, and the wattage of your circuit, you could do the math that way. It's going to line up the same as the current there, whichever one is more useful for whatever reason. So, in any case, yeah, this is important to know if you're going to start using cells or batteries. You know, there's whatever cell or battery you're putting together, these basic principles apply to it, although real world putting them together is more complex. There are holders where you can put like cells in series. If you're using certain types of batteries, you might be you know, welding them together or bolting them down or something. There's all kinds of ways to connect them. This is just the basics of what the parallel is, what the series is, and then just realize instead of cells here, a single cell here, you could have parallel cells. But again, they have to have the same voltage as each other and the same capacity, the amount of current they can provide right there. Because remember, each one of these is providing the same current when they power a load. So they have to discharge at basically the same time. And if they're rechargeable, recharge at the same time. Because if one is charging faster than the other, then it's going to overcharge. And there's protection circuitry for that and whatnot. So it's kind of complex, but once you learn all of this stuff, it's actually pretty simple. It's not too bad. So hope you enjoyed. Make sure you check out one of the other videos I posted on the screen and check out the links down below. They all help out a lot. I'll see you in the next video.